before we go into the basic principles of optical remote sensing, and we'll see why we say optical remote sensing instead of remote sensing. So if there are no questions, I'll continue with this part of the presentation. Now, what are the basic things that we all need to know when using remote sensing? Well, first, this concept of electromagnetic spectrum, which is that we are surrounded by electromagnetic energy. It's a form of energy that travels in waves, and that includes from very, very high frequency and short wavelength to very long long wavelengths and low frequencies. And low frequencies, yes, where we have the radio and the TV applications. We have a number of applications. We'll be concentrating only in the visible electromagnetic spectrum. This comes from a radiant source like the sun, and this reflects, or this travels as light in different wavelengths. So this is like the visible range of light, and we define this as the range of all possible frequencies of electromagnetic radiation, in which we have different forms of energy. Light is from the sun is one. So we'll concentrate only in the visible region, or near visible region, which can tell us a good story about the objects that reflect the lights. So we'll have that different objects will reflect light in different ways, which is why we use satellites to recognize different types of objects. And we call this optical remote sensing because basically it's based on the optical features that are related with the reflectance of the different wavelengths that compose light. You could have other types of sensors, active sensors like radar sensors, that they will emit or issue a sound, and this will be captured by the sensor itself. So that's active because it's issuing a wave and then capturing that wave. LiDAR is a very interesting technology that works in the I think it works in the UV ranges. So those are examples of active sensors. We're just going to be passive sensors, which just capture what light is reflected from different objects. So this is a basic concept. This is where we're going to be working, and that's why we call it optical remote sensing, and we call it remote sensing from now on, for short, for brief, for being more brief. But it's what we're doing is capturing the different wavelengths of light. And when we talk about vegetation, then you have different objects. We'll have a similar behavior across vegetation in general, which is vegetation has chlorophyll, and this particular feature of vegetation, it's capturing blue and red wavelengths, or wavebands, I mean. That's why we don't see, because it's absorbing those wavebands, and that's related with the color of the plant. That's why we don't see blue or red plants. That's because they are capturing that light, and they're reflecting the other wavebands in the green area. So that's one concept. The other concept is that biomass of the vegetation, it's related with the near-infrared wavebands. So that's reflecting the near-infrared ranges. So this is what we're going to measure with the imagery, and this is all going to make sense when we start looking at the bands that are captured by the satellites or by the aerial or by the unmanned aerial vehicles. what they do is they measure the disappearance of red light and the abundance of reflected near infrared wavebands. So we see that different crops will have similar behavior, but will have different degrees of reflectance. So you see here that alfalfa, beans, grass, potatoes, corn, soybeans will have similar behaviors between if you remember, this green to yellow areas have high reflectance, then below that or above that it's low reflectance, and then also there is a reflectance of the other wavebands called near infrared above that. So with that basic principle of how they behave, and this is applicable to any object, that's why this is used in geology, it's used in many applications. For instance, here you have a yellow line that's wheat stubble, or you have a purple line that's dirt. I'm just going to mark it. So this has a completely different behavior. So just by knowing this, we can do a number of applications. We can differentiate crops, for instance, and we can do several applications with different indexes based on this basic principle. One of the most, and this is just an overview, and we'll review all these indexes without getting too complicated, but just to understand how it works and then how we read information from this. So normalized differential vegetation index is it's one of the indexes that's most widely used, and this will compare the reflectance of the red and the near infrared regions of the electromagnetic spectrum. So you have here a case of a healthy plant and a plant that's in the fall season or has stress, where you see that the near infrared that measures biomass has a higher degree of reflectance, and the visible wavebands, remember the green and the green bands, are absorbed by the plant, where in a crop with stress this is not as much as absorbed by the plant, it's more reflected. So combining these two basic concepts, it's so it's as simple as that. It's different wavebands that are reflected on the plant, it's captured by a satellite, and then we combine this when we process the imagery. So this is one of the indexes that we're going to use. So I hope I wasn't too confusing regarding this explanation, but basically we're going to measure different values of reflectance of the different wavebands that we capture through the satellite. And as we start working, this will become more familiar. So if there are any questions, please go ahead, and otherwise I'll just continue with a little bit more information. Okay, remote sensing systems. When you go to the market and say, okay, this is SPOT, this is Politis, Rapid Eye, and the many different satellite systems that you see, or you speak with your local aerial imagery provider, or you speak with maybe unmanned aerial vehicle in the future, you'll have these three basic concepts. Spatial, what's the resolution? What's the pixel size of the image? What's the spectral resolution? That is, what bands do you have? So that's why we call this, or we use multi-spectral imagery, which means it's an image that with special sensors captures different bands of the wavebands, or I mean of the ranges. Usually you'll see that each specification has a range of wavelength that is captured by the bands of the imagery. And temporal resolution is how often does it visit. And so we'll see in the different applications that we'll review during the course that you'll have some minimum requirements for a spatial resolutions, for a spectral resolution, or how often you want to visit. For instance, in crop protection, in some critical area, times of the year, you need to do frequent visits, just to give an example. Or if you're going to use imagery to support your crop scouting, you as an agronomist know well when you should visit, and the imagery should be in that time window. And this is an interesting figure that I found in a book that's more than 30 years old. The same concept applies, the technology has changed. You see here, this it says in the x-axis is spatial resolution. So you have all the way from 10 centimeters to 100 kilometers. And in the y you see temporal resolution, how often does it visit. So if you're going to talk about the weather, it's enough to talk about between 5 and 100 kilometers. But you need to have frequent updates to be able to describe and predict. If you're going to talk about geology, that doesn't change much. So maybe 100 years you will do a geological study, but you need much higher accuracy. In crops, this is where they located it at that time, which is in the 10-meter range, somewhere between 10 and 30 or 5 and 30-meter range, and in the weekly updates. This is moving more to the left now because we're having higher resolution. Maybe the temporal resolution cannot be much better than every week, but the spatial resolution, it's getting better and better every year. So, and this is interesting. You see here this dotted line is data volume threshold. That's because the systems and the technology was not able to handle more data below this threshold. This looks like a American football chart where you have so many errors that you don't understand anything. But you see here in this data volume threshold, now this line is moving more to the bottom where we can manage more data, we can download faster, we can process faster, we can store more. So that's how the way things are moving. So with this very general figure, let's look at, and we'll be reviewing this in the second week. We'll be actually looking at examples. These are just some examples of remote sensing systems. There's a longer list, but Landsat, which is a free resource, is very widely used. Unfortunately, it's out of service 2012. It has 7 bands, has 30-meter spatial resolution, and visits every 16 days. RapidEye, which is a German system. It's 5 bands and 5 meters resolution, typically 15 days, but it can vary. When you have commercial satellites, then you can play a little bit with the tasking. We'll have we'll introduce next week some of the company called Astrium, which is the same company that builds the Airbus plane. They also have satellites. We'll be reviewing Spot 6 and 7, which is coming next month. That will be a big improvement in terms of resolution. And they have launched Politis earlier this year at 50 centimeters. So we're seeing more and more, and next week we'll review this in more detail. But basically you have number of bands, spatial resolution, that's number of band or spectral resolution, and that's why we call this multispectral, spatial, and temporal. There's also something interesting about satellites, which is its swath width, which is what area does the satellite cover. And this has to do with when you have regional projects, you want to look at this, you know, how wide this is, because that will have, and usually at higher resolution you have less coverage, and at lower resolution you have more coverage and lower cost per acre or hectare or square kilometer. And then something interesting is the aerial and unmanned aerial vehicles. I'll see if I can invite a aerial imagery provider to tell us about his experience in Nebraska. And that can vary from 20 centimeters to 1 meter depending on the flight height. They can also use multispectral cameras in their systems. And this is the advantage, and we'll be comparing this in more detail. The temporal resolution can be upon request because they don't depend on the satellites passing over the Earth. they can just fly. It's more expensive, but it's for some application it's more time critical and more useful. So we'll be reviewing these differences. Okay. Any questions so far? Just let me know and we'll address them. Okay, so